All right, welcome students to lecture 12. In this lecture, today I'll be discussing about the lattice vibrations of for a diatomic lattice. So that means this is a lattice with a basis where the basis has two atoms. So this is what we'll cover: lattice vibration and normal modes of lattice vibration for a diatomic lattice. Okay, so monatomic lattice we have seen earlier, right? We have looked at the dispersion relation, and we have seen that the dispersion relation is periodic, right? So we have seen that the frequency has a maximum at the zone boundary, right? So we have considered the longitudinal vibration. Now let us consider the similar situation but for a diatomic lattice. So that means each lattice point has a basis of two atoms. So let us consider this. Again, we consider one-dimensional lattice. Now we consider let's say two lattice points. Each has two atoms, so let me consider blue atoms, and possibly we consider another small red atoms, something like this. Okay, so if you want to imagine, so this is possibly your lattice points. These are your lattice points, which is a basis of two atoms, right? And let us consider this red atoms. The blue atoms have mass, let's say m, and the red atoms, the small atoms, have mass small m. Okay, these are the atomic mass. All right, so now our lattice constant would be this. Now it is, let us consider this as, we call it a repeat distance, or the lattice constant in this case. Let's say this is 2a in this case. Okay, so let us consider this. This is the 2a, right? Similarly, the other cases it's all 2a. Okay, so we are considering this, and so this is from blue to blue, right? Greens, what are the greens? Greens are the lattice points. So I'm removing this so that you are not confused later. So these are the two atoms, blue atom and red atoms, right? And so again, so these will be, let's say we consider them as connected by spring. Okay, something like this. All right, so what we consider now here, the distance or the positions, right? So let's say this is 2r, and this point would be, this red one would be then, let's say 2r plus 1th atom, right? So this is then 2r plus 2 and so on, and this will be then 2r minus 1, this red atom 2r minus 1, and blue atom is 2r minus 2. Okay, so this is, we are considering these 2r. These are just for simplicity of our calculations. Remember there are red atoms. So let me make this so that red atoms and blue atoms. All right, so now as we have written right earlier, so we will now write the equation of motion, and what we have considered is the 2a is the repeat, we call it a repeat distance in this case, in this case. So now we look at the displacement of this atom, right? So we are again considering longitudinal displacement. So what we are considering now is that there are two atoms at each lattice points, right, who are now undergoing longitudinal oscillations. The last two atoms, right, edge atoms, are clamped. Okay. We know it for individual atoms, for the single atom basis, right, for the monatomic lattice, I mean, right. Now we are considering for the diatomic lattice. So this is UR, and this will be then let's say 2R plus 1, right, and so on. So we write the amplitudes, displacement amplitude, which will oscillate, right? So because of this oscillation, as we have discussed earlier, let's say U2R equal to e to the power I, right? Now because it is 2R, so rth atom, so this is now 2, or for your understanding, so Q times 2R into A, right, the distance from the origin, let's say. So this will be 2RA minus omega t, right? And for the other one, U2R plus 1 will be equal to B e to the power I. Now let me write it, 2R plus 1 Q times A minus omega t. Okay, so let's say we number them as equations 1. Okay, so we are considering the two atom bases, right, and then we are writing the displacement equation for that. And now if we consider only the nearest neighbor restoring forces are important, and then the oscillations are small, so then we can consider them that they are displaced during oscillation. The displacement will be within the elastic range of Hooke's law, right? So then the force equation would be, if you consider this, then the force equation, as we have written earlier, would be now given by m omega square u twice r will be equal to m d2u 2r dt2, right, which will be equal to mu eu 2r plus 1 plus eu 2r minus 1 minus 2 eu 2r, right? So you remember, I've not retained, I've just skipped one or two steps here, sorry. But you know all the meanings, right? We have just done this in the last class, right? What is mu? Mu is the force constant, right, which we are considering. So this is for one atom, and the other atom with larger mass will be m omega square u 2r plus 1 equal to m dt u 2r plus 1 and atom dt square equal to mu u 2i's r plus, now it will be 2 plus u 2r minus 2 u 2r plus 1. Okay, so I hope you remember that. So what we did here is basically the force, the displacement equation which we have written, right? We have taken the double derivative from here, right, and which we have considered with the force equation, right, where we have taken the mass and acceleration from the displacement here, right? So this is what we have done earlier. So now we are writing it for the two different atoms, right? So two different atoms are displaced in a different way. So therefore we are writing the two equations. And now if we substitute, so this is number 2. Now substituting one, the displacements in 2, right? If you check that, so you'll see that this will be given by minus m omega square times a equal to mu b times e to the power I qa plus e to the power minus I. So remember, q is the Phonon wave vector, right? And minus 2 mu a. Okay, and the other one would be capital M omega square b equal to mu a, would be again e to the power I qa plus e to the power minus I qa minus 2 mu b. So so these are the two equations we would get. Now let me write it as number 3. Right. So now we can rearrange. We have to try to find the coefficients of a and coefficients a and b, right? So we try to rearrange. So we can write it as a times 2 mu minus m omega square will be equal to 2 mu b. Now e to the power iqa plus e to the power minus iqa, so that would be then 2 cos of qa, right? The other one would be then b times 2 mu minus capital M omega square will be equal to 2 mu a cos of qa, right? So these are the two equations. Now the equation number 4 that we are getting, right? So let me go back to this. What we are considering is 2r is the position of the sorry, let me put it other way around. So let's say the mass of the atom, 2rth atom is capital M, right? And mass of the 2r plus 1th atom is the small m, right? And then because of this longitudinal oscillation, as we have discussed earlier, now the two atoms which are vibrating, so we are considering u2r plus 1, right? And then the fourth equation which we have written earlier, right? So that you know, and we are now writing it for the two different equations. So 2r we have considered for small m, right? So let me see, 2r for some I see. So here I think we have to, I've just changed it actually. So this would be for 2r is the small m, so I think we have to shift one. So this is small m and this is capital M, and so on. This will be plus 2 and this will be plus 3. This is minus 1. Okay, so nothing changes. I have just changed it. I think in this equation I have written 2r for the small mass, right, and 2r plus 1 for the capital larger mass, capital M. Okay, so this is capital M, 2r plus 1, right? And then substituting this u2r and u2r plus 1 from number 1, then we get these equations. So which we are now trying to solve, right? So So to solve this, right, if you try to solve this for omega square, right, we'll find that 2 mu minus m omega square times 2 mu minus m capital omega square would be equal to 4 mu square cosine square QA, right, from 4. Okay, so we are multiplying these two equations, and then this is the expression that we get, right, from number 4. Okay, so therefore then now if we solve this, we'll get omega square, which I am writing it for you. So this will be mu times 1 upon small m plus 1 upon capital M, right, and plus minus mu it will be 1 upon m plus 1 upon capital M whole square minus 4 it will be then sine square QA by small m capital M, right, the square root of this. Okay, so this is the solution that you will get. You will solve this. Please check that. I've just skipped 2-3 steps here. Okay. So now, so this is an important expression, right? So this is a relation between omega versus q, as you see, which also shows an oscillatory behavior. This is a sine function here, right? So if you remember, for the monatomic case. We had the result, right? So we had for monatomic case we had omega will equal to 2 root over mu by m. I hope you remember, right? And sine of QA by 2. Right, and this is the solution for the now the diatomic lattice, right? Both are the function of sine QA, but here what you see for the monatomic case is that for one single Q value there is only one frequency, right? So whereas here for the diatomic lattice, now you have, for a single Q value you have 2 frequencies. Right, given by this plus minus sign here. Okay, so that means we have now 2 values of q omega. Now for diatomic lattice, we have now 2 values of omega for a given q, right? Given q, even in the positive quadrant. Okay, so what it means is that if you look at the spectrum now, so let me draw it, right? So this, that is q, right, and this is omega, right? So now let me go back to this. So what is maximum omega? Let's say we have now omega values as omega and omega plus and omega minus, let's say, right? So we have two values, let's say omega plus and omega minus, right, corresponding to these plus and minus values here, right? So for omega plus, the maximum value and okay, so we can write it for omega plus, the maximum value omega plus max will be mu times 1 upon m plus 1 upon capital M, right? Square, thing like that. Okay, so oh no, so this is omega squared, so this will be omega square root of this half, right? So this is the so there are two frequencies now corresponding to one Q value, right? One is of higher frequency and the other is the lower frequency, right, which is omega minus. So now let us try to understand what this means. Okay, so if you now I'll come back to this plot later. Okay, sorry. So now omega will be equal to, or omega minus, let's say omega minus will be equal to root over 2 mu by m. Okay, considering if m is very much greater than m, small m. So omega plus we have calculated, right? The maximum value is given by this. Now we can find out if the capital M is very much, so we can find out omega plus max how much if capital M is very much greater than M. So one atom is much higher mass than the other one, right? So we can find this out, right? So easily. Okay, so similarly, the other case what we are finding out is that what is omega minus max. So omega minus is actually the lower frequency, and that is similar to the acoustic wave that we have discussed earlier. Okay, so if we plot the second one, that is omega minus, as a function of Q, right? So and if, so we can simplify this with capital M very much greater than, very much larger than small m. So in that case we can, so this will be the mu by m minus here 1 mu into 1 by m upon this, right? So this you can solve, and if you plot this, you will see that this is of similar mass and similar behavior, but this zone boundary is now pi by 2a. Okay, so if you solve this, and for Q correspond to pi by 2a, you get the maximum. I'm skipping this calculation, but this you can check very quickly, right? So you will have a maximum, so something like this here. Okay, so similarly corresponding to minus Q, you will have something like this. Okay, so it's not symmetric, but it should be. Let me see if I can be a little bit better. Okay, so this corresponds to omega minus. Okay, and what is the maximum value? This is maximum. So this corresponds to 2 mu by m square root of this. Okay, for m very much greater than small m. Okay, so the other frequency, omega plus, right? So maximum value we can calculate, right? So this is 1 upon square root of 1 upon m basically. So this will be then, if you plot this, you will see for Q equal to 0, that frequency omega is not 0, right? Because this is plus omega plus, right? So omega plus is not 0 at q equal to 0. So if you plot this, you will see that there is a certain frequency, certain mode at long wavelength. That means omega q equal to 0, and the mode behaves like this. Okay, so now you see that corresponding to so this is now omega plus, and as I said, this one is omega minus. Now corresponding to each q value, right, corresponding to each q value, as I have shown earlier, now you have two different values of omega plus and omega minus, right? And the maximum value of omega corresponding to particular q value you can calculate from this expression here. So let me write this expression as 5, right? So from 5 you can calculate this. So what you see here is that when q equal to 0, omega plus is not 0, right? So therefore it is a higher frequency. So that means at very small long wavelength, these kind of frequencies can be excited. So what is the significance of this? So these are called two branches, right? So one is called the higher frequency one is called the optical branch. Omega plus q is called optical branch. I'll tell you the reason. And omega minus q is called acoustic branch. Okay, and there is a gap, energy gap between the between the two frequencies, right? At any given q value. So, and this is forbidden. So that means within that range, that frequency range, no mode can be excited in the system, right? In the diatomic lattice. So now let us try to see what this means. Okay, so now for q equal to 0, if we substitute u in if you substitute u in the displacement equation, so that means, let me show you. So if you now consider q equal to 0, for example, right? So from here, if we substitute this these values to the equation of motion here, right, in equation 2. So let me write it for q equal to 0. If we substitute 1 in number 2 in equation of motion, right? So what we'll find? You'll find that u u2r. So let us do this, or maybe write it here. So u2r q equal to 0, right? Q equal to 0. So it is a e minus omega t minus I omega t, and here also for q equal to 0, this is b, right? So that means u2r equal to u2r plus 1. So this is basically a equal to b, right? So this is basically you can write it like this: a equal to b, right? This is for the acoustic branch. So acoustic branch means omega minus q for omega minus q. Okay, so what we are doing is that we are writing the omega minus value, right, and we are putting for q equal to 0, so that means q equal to 0 in this equation, right, and then we find that a equal to b. Okay, whereas for the optical branch, so this means this is for the acoustic branch, whereas for optical branch, that means for omega plus q, where q equal to 0, so that means q equal to 0, we are putting it once we put there, so then we'll find that minus so a by b will be equal to minus small m by capital M. Okay, right, so that means in the optical branch, in the optical branch what we see here is that both these two masses, right, they vibrate opposite to each other, right, so a and b are these are the coefficients of these vibrations, so they vibrate opposite to each other. So what it means here is that now in the acoustic branch, so in the acoustic mode, that is the low energy, low frequency or low energy mode, a equal to b, so that means both atoms, they are vibrate in phase. So that means let's say vibration, let me show it like this. So then we have, you remember we had red and blue ones, so red, let's say red, and then we have small blue, so they are vibrating along each other. Okay, so this is the acoustic mode, right? So that means, what it means is basically that the neighboring atoms in these atoms are in phase, right, because it is a equal to b in this case, right? And whereas for optical modes, let me draw it to the other side. Optical mode, so that means omega plus q, right? So which is the higher frequency. Frequency mode. So there we see, because you know a by b equal to minus, I think, small m or capital M, just check that. So the meaning is that they vibrate opposite to each other. So that means, now let me consider this. Right, and one is the red atom, so that means the red atom is here, let's say here, right, here, right, and then we'll see the so they're opposite in phase. Right, so the blue atoms which were here, now it vibrates here, right, and this vibrates here, so this would then vibrate somewhere in this phase, right, so this would then vibrate in this phase, this would vibrate along this. Okay, so that means so red ones are the bigger ones, right? So you remember I've just not drawn it, I think, properly, right? So these are the mass m, and this is small mass, right? So that means they're vibrating opposite to the phase. So that means here for the optical modes, neighboring atoms, they vibrate out of phase in this case. Okay, so this is what we learn when we have two atoms at one basis. What we see here is that if we consider only the longitudinal oscillation, of course, as I said earlier, that the transverse oscillation is there, but we are only studying the longitudinal oscillation. So what we see here is that now there are two modes of oscillations corresponding to each wave vector. Right, at one wave vector there can be two modes at two different frequencies, right? So the lower one, which is called acoustic mode, which is linear in the low wave vector or high large wavelength regime, which is linear, right, which is a maximum which we have calculated. We have just considered capital M is much smaller than small m. This just helps us to simplify the the expression. Otherwise we cannot calculate that. We know how to do that, right? So now we have considered the acoustic mode, and we are trying to see how these two atoms are vibrating, right, in the acoustic mode. So we see that the acoustic mode means that the oscillations are in the same phase. We find that for q equal to 0, that is for long wavelength, right? This is for the long wavelength case, you remember. So for the long wavelength case, we see that the vibrations are acoustic vibrations. For the acoustic wave, two atoms vibrate in phase, neighboring atoms vibrate in phase, whereas in optical mode we see that corresponding to q equal to 0, that is long wavelength mode, the neighboring atoms vibrate out of phase, right? So that's what I have tried to show you here. Why are they called optical modes? Because if these two atoms, if these red atom and the blue atoms carry opposite charge, let's say plus and minus q, for example, then actually these kind of oscillations can be excited by using electric field of a light wave. Okay, so typically in the infrared region, for example, if you can shine light of that energy, right, or electromagnetic wave of that energy, right, so you can excite this kind of mode, right? So remember that this is the high frequency mode, right? So therefore these are called optical, so this branch is called the optical branch. Okay. Okay, so so at the zone boundary, what we see here, so these are the two modes, two branches we understand, right, corresponding to this q equal to 0, right? Now you see, if we go back to this, we see that at the zone boundary, now remember zone boundary is at pi by 2a. What is 2a? 2 is the repeat distance, right? So in monatomic lattice, you remember that is zone boundary is pi by a, we have considered, right, because a is the lattice constant. Here the lattice constant is actually the repeat distance between the two equivalent atoms, right? Distance between two atoms of capital M mass or two small atom of m, two atoms of mass small m. This is all 2a, right? So therefore the zone boundary is at pi by 2a. Now you see that at the zone boundary there is a gap, right? There is a frequency gap at the zone boundary of the first billion zone, and yeah, so this is called the forbidden band. Okay, so now in summary, right, so what we find is that there are two branches, right? One is the acoustic mode and another is the optical mode corresponding to one q value. Now at q equal to q very small, right, we see that for the acoustic mode omega is almost tends to 0, right? However, in this long wavelength limit, optical modes can be excited, right, of very large wavelength. These optical modes, they interact strongly with electromagnetic radiation, right, in case of polar crystals, meaning that if the two atoms have opposite charges, they are polar. In those kind of crystals, you can shine electromagnetic waves, and then these lattice interact strongly, and they can be excited, right, with these kind of. So therefore, the strong optical absorption is observed actually in this kind of cases, right? So because the light is or the radiation is absorbed to excite this kind of phonons. Okay, so that means what we can say that the photons are absorbed, right, or annihilated, and phonons are created in these kind of cases, right? Okay, so we can write for optical modes. Right, they interact strongly with electromagnetic radiation. Remember, in polar crystals. Right, and so this is one. Optical modes omega is non-zero, right? So there is certain finite omega for Q tends to 0, right? Whereas acoustic mode, this is omega is 0. Okay, so now we can try to see at the zone boundary, right? So zone boundary mode. So this is all at Q equal to 0. Now at zone boundary, Q equal to pi by 2a, right? So pi by 2a, so Q is 2 pi by lambda. So this implies your lambda is equal to 4a, right? So this is the wavelength for the zone boundary, right? So what we can see here, what we can see here is that at the zone boundary, the acoustic branch, that is acoustic branch that you know, right? There the small particles, that is the particles of small mass, are all at rest. Okay, whereas for the optical branch, the heavy particles of mass of the heavy particles are at rest. Okay, so so this is the observations that one makes from this calculation. So at the zone boundary, lambda equal to 4a, right? So high energy modes. So that is the let me. Energy mode at the zone boundary. So if you use these values of Q, right, in the displacement equation, you will see that only the atoms, only atom with mass m moves. Okay, so you use this q equal to 2 pi by twice a in the displacement equation, and then you will see that only the atoms with capital small m moves, whereas atoms with mass capital M, the larger atom remains at rest. Okay, so this is corresponding to higher energy, so that means omega plus. So omega plus we know, right? And q we are defining as pi by twice a. So you put these two values in the displacement equation, and you will see that so what is the displacement equation? This is here, right? Here. So you use both omega plus and q equal to pi by a, then you will see that here the heavier mass remains at rest and the lighter mass moves. Okay, so please check that and verify that that yourself. So similarly for lower energy mode, at zone boundary, meaning again q equal to pi by twice a, then you will see only in this case, let me write it in red, only heavier atoms move, right, or oscillate, right, whereas the light particles, lighter atoms mass m are at rest. Okay, so please take it as an assignment and then try to do this. I've told you, gave the hint how you need to do that, right? So please check that and then try to satisfy yourself. So I think with this, I would like to finish it in this today. Finish the Phonon modes where we have considered very simplistic cases or one-dimensional chain, right? For first we have considered the one-dimensional chain for infinite atoms. Then we have considered what happens if the atoms are two atoms at the edges are fixed, right? And then now we have considered the diatomic atoms, right? At each atom, at each lattice point there are two atoms, and we see that if you do that for the diatomic lattice, then you see that there are two branches, acoustic branch and optical branch appears, which is of optical branches of higher frequency, right? So we have considered the two cases at the zone center, that means at q equal to 0, so there, which is actually high wavelength, large wavelength mode, where the acoustic acoustic mode or the frequency is almost 0. However, there is a optical mode which can be excited at very large wavelength, right? Why are they called optical branches? Because these are the modes these are the high frequency mode which can interact strongly with electromagnetic radiation, and as I told you, the electromagnetic radiation can be absorbed. That means photons can be absorbed, and these optical phonons can be excited at this kind of frequencies, right? Then we have considered at the zone boundary, what happens at the zone boundary. So now remember, the zone boundary is at pi by twice a, not pi by a, because twice a is the repeat distance now. Okay, yeah, and then we have considered what happens for omega plus and omega minus. That means for high energy and lower energy mode, right? What we have now figured out that the atoms, heavier and lighter atoms, they behave differently at the zone boundary, right? So for optical modes, the lighter ones move right? They oscillate, and the heavier ones, they are at rest. Whereas for acoustic waves, heavier atoms oscillate, but the lighter atoms, they are at rest. Okay, so please check that and try from the displacement equation yourself. Okay, so with this, I finish it today. If there is any question, please feel free to discuss with me. Okay, thank you very much. By the way, so this will be also part of your exam. This will be included in the syllabus, exam syllabus. Okay, thank you.